The second example of a digital logic circuit is a latch, a circuit with memory. So let's explain how that works. So in general, sequential logic is logic with memory. So the point is that past values must influence present values of signals. So we need a way for the past to influence the present, and this is called memory. So here's an example of how we could do this. We have two signals, S and T. Now assume that we want the past to influence the present. So for example, A0 should have an influence on B1. So this is the past, time 0 is the past, time 1 is the present. And A1 should influence B2. And A2 should influence B3. So each past moment has to influence the present moment. So if we see what that means in general, it means that BI is equal to A of I minus 1. So this is an equation between elements of streams. Now if we see what this really means, it means that the stream is shifted over. We can say, for example, the stream T is 0 bar S. That means that the S is shifted over into the present, from the past into the present. We have to add a 0 element here at the left. So for example, here we could say B1 is equal to A0, but what is B0 equal to? We have to give it an initial value. So we can say the initial value is 0. So this means that the delay gate, the gate that calculates this, actually has a very simple implementation. The delay gate of S is simply 0 bar S. And so we can use this delay gate now to build circuits with memory. So here's a simple circuit with memory called a latch. It has two stable states and it can memorize the input. So we have here an input signal and an output signal. And the input signal, there's two possibilities. We have here a C, a clock, which controls how the input signal and the output signal are related. So if the clock value is 0 here, this makes it a 1 here, and in the value E, that means the output is going to be equal to the input. If the clock value now turns to 1 here, 1, that means we now have a cycle here from the output through a delay, so the past to the present, going back to the output. So the output will freeze into the previous value it had in the previous instant. So it's a memory. It will freeze as long as we keep the clock equal to 1. If we bring the clock back to 0, then the DO will again track the input the same instant, and we bring it to 1, it will freeze into the value of the previous instant. Okay? We can implement this now in a simple way as a component. Notice the similarity in the form of this with the full adder. We have a procedure with 3 arguments. These are the 3 visible wires and 4 internal wires that are not visible from the outside. We have a delay gate, an AND, a NOT, an AND, and an OR gate. And again, I'm going to ask you a question on this latch. When we create a latch, by calling latch, how many threads will we create?